Your pocket is holding the biggest network ever built. Open any social app and look past the interface. Every account is a dot. Every follow is an arrow from one dot to another. 2 billion dots, hundreds of billions of arrows, things pointing at things, exactly the shape none of our structures could hold. The formal names are simple. The dots are called vertices. The arrows are called edges. Together, a graph. And you already know the first real distinction by instinct. A follow is one way. You follow a celebrity. The celebrity does not follow you back. That arrow has a direction, so the follow graph is directed. Friendship, on the older networks, is mutual by construction. Accept a request, and the edge points both ways at once, an undirected graph. Same dots, different kind of arrow, and the choice changes which questions even make sense. One more piece of vocabulary you've carried for years without the name. Your follower count is just the number of arrows pointing at you. Graph people call it your in degree. You've been fluent in this longer than you think. And once you have the two words, you see them everywhere. A road map. Vertices are intersections. Edges are road segments. And each edge carries a number. The distance, or the minutes. That's a weighted graph, and every navigation app you've used is asking it for the cheapest path. A path being a sequence of hops, vertex to vertex, along edges. Next, a package dependency graph. Run an install, and your project pulls a library, which pulls 3 more, which pull more. Vertices are packages. Edges are depends on, directed. And here's a property worth a name. Follow edges and arrive back where you started. That's a cycle. In a social graph, cycles are everywhere and harmless. You follow her, she follows him, he follows you. In a dependency graph, a cycle is a disease. A depends on B depends on A. Neither can build first. Real package managers refuse to install one. And how you detect a cycle is a traversal question. Next lesson's business. Even the tree from the last 3 lessons fits here. A tree is just a graph on its best behavior. One parent each, no cycles. Drop those promises, and you've arrived. So, how do you store one in memory? Don't wave at it. Be concrete. Here are 6 users. Ava, Ben, Cleo, Dev, Ina, Finn. 8 follows between them. Ava follows Ben and Cleo. Ben follows Cleo. Cleo follows Ava back. Dev follows Cleo too. She's the popular one, 3 arrows in. Ina follows Dev and Finn follows Ina back. That's the entire graph, and every example for the rest of this lesson is this graph. Now feel the actual problem. An array was easy to store. The structure was the memory layout. 1 block, done. A tree had 1 parent per node, so each node carried a couple of pointers. But here, anything can point at anything. Cleo has 3 followers and follows 1 person. The shape is irregular by nature, and memory is 1 flat line of bytes. Bridging those 2 facts has 2 classic answers, and they sit on opposite ends of a trade you've known since the very first lesson. Memory versus time. Pay storage up front to make questions cheap, or stay lean and pay per question. Answer 1. Give every user a number. Ava is 0, Ben 1, Cleo 2, Dev 3, Ina 4, Finn 5. Now build a 6x6 grid. Row I, column J, holds a 1 if user I follows user J, 0 if not. This is the adjacency matrix. Ava follows Ben and Cleo, so row 0 has 1s in columns 1 and 2. Cleo follows only Ava. Row 2 is a single 1, then zeros. 8 1s, 28 zeros. The whole graph in 1 rectangle of bits. Now ask it questions. Does Dev follow Ina? Row 3, column 4. 1 multiply, 1 add, 1 read. 0. No. That's an order 1 edge check. The fastest possible answer, no search involved. Who does Ina follow? Walk row 4, all 6 cells. Zeros, a 1 at dev, a 1 at fin. Listing neighbors costs order v, the number of vertices that exist, even when the answer is 2 names. And lesson 2 gets a word here. A row is contiguous memory, scanning its streams, line after line, the pattern the prefetcher rewards. But ask the reverse question, who follows Clio? And you're scanning a column, a strided walk, the exact villain from the grid race in lesson 2. Same data, same big O, physically slower steps. In space, 6 users cost 36 cells. Notice what that number depends on. Not the 8 follows. 36 is 6 squared. The matrix charges v squared cells whether the edges show up or not. So price it the way lesson 1 taught us, at real scale. 1 million users. Each follows 200 people on average. The matrix needs 1 million rows times 1 million columns, 10 to the 12th, 1 trillion cells. At 1 byte per cell, that's a terabyte of memory. Pack each cell into a single bit, the matrix's favorite trick, and it's still 125 gigabytes. Now, how many of those trillion cells actually hold a 1? 200 follows times 1 million users. 200 million. 200 million out of 1 trillion. 0.02%. 99.98% of that terabyte stores the word no. There's vocabulary for this. A graph with few edges relative to v squared is sparse. One approaching v squared is dense. And almost every graph reality produces, social networks, roadmaps, dependency graphs, is sparse. The matrix prices itself for the dense case, and reality keeps refusing to be dense. Answer: 2 stores only what exists. Keep 1 slot per user. In Ava's slot, the list of who Ava follows. Bin, Clio. In Bin's slot, just Clio. Clio's, Ava. Dev's, Clio. Ina's, Dev and Fin. Fin's, Ina. This is the adjacency list. Count the storage. 6 slots, 8 entries. 1 slot per vertex, 1 entry per edge. Order V plus E. Run the arithmetic again. 200 million entries, 4 bytes each. 800 megabytes. Call it a gigabyte. Against the matrix's terabyte, 1,000 times smaller, because nobody is paying rent on the zeros. Same questions, new prices. Who does Ina follow? Read Ina's list. 2 entries, done. Neighbors now cost the degree, the edges you actually have, not the vertices that exist. Hold on to that one. Does Dev follow Ina? Scan Dev's list. Also order degree. 1 entry here, maybe 200 on the real network. The order 1 edge check is gone. That's the price. 2 honest notes. The textbook drew these lists as linked nodes, lesson 5 style. Modern implementations use dynamic arrays, lesson 3. Contiguous, cache-friendly. And when vertices are strings, usernames, package names, the outer array becomes a hash map, lesson 12. So line them up. Edge check, matrix, order 1, list, order degree, enumerate neighbors, matrix, order V, list, order degree, space, matrix, V squared, always, list, V plus E. The rule falls out. Sparse graph, edges far below V squared, take the list. And since reality is sparse, the adjacency list is the default representation of every graph you will ever touch. So when does the matrix earn its rent? Genuinely dense graphs, rare in nature, common in machine learning, where models multiply adjacency matrices outright. Tiny fixed graphs, a game board in embedded code, where 36 cells is nothing, and order 1 probes are pure profit. Workloads that hammer the edge check millions of times a second. In one famous algorithm family, all pairs shortest paths, Floyd-Warshall by name, works directly on the matrix, a DSA pattern story. One more representation deserves a sentence. Just keep an array of the edges themselves. Ava Bin, Ava Clio, 8 pairs, nothing else. The edge list. Terrible at queries, but it's how graph datasets ship in files. And one classic algorithm, Kruskal's, wants exactly this form. Sort the edges, take them in order. Also waiting in DSA patterns. Now the real systems. Your following list and your followers list on the actual platform. Both adjacency lists, stored twice. The graph and its reverse. A list only answers questions in the direction it stores, so the platform materializes both. One profile load, one list fetch. At Facebook's scale, that store has a name, TAO. An entire service whose job is roughly, given a vertex, return its adjacency list, fast, from a graph too big for any one machine, so the lists are sharded across thousands of them. Hedged in the details, but that's the shape. And nobody at social scale has ever built the matrix. The terabyte arithmetic is why. Package managers, same picture. Your manifest names your dependencies. Those are your out edges. The resolver fetches each dependency's manifest, which names more edges, and walks outward until the graph is closed. The lock file it writes is that adjacency, flattened and pinned. Cargo, like most resolvers, runs the cycle check from earlier and refuses a cyclic graph. Build systems too. Make in the 80s, turbo repo today. A task graph where edges say, build this before that. 3 different products, 1 representation underneath. One more idea, and it pays forward. Sometimes the graph is never stored at all. A maze. Every cell is a vertex. Edges connect cells you can step between. Nobody builds the adjacency list, because given a cell, you can compute its neighbors on demand. Up, down, left, right, minus walls. The graph exists the moment you ask. Word ladder puzzles, same trick. Words are vertices, edges connect words 1 letter apart, and the neighbors of cat are computable, not stored. And the extreme case, a chess engine. Vertices are board positions. Edges are legal moves. That graph has more vertices than the universe has atoms. No representation on Earth holds it, yet engines explore it every day, conjuring each position's neighbors exactly when needed and letting them vanish after. This is called an implicit graph, and it tells you something important about what's coming. The algorithms that walk graphs don't care whether the edges were stored or computed. They only ever ask one question. Give me the neighbors of this vertex. Which is the door to the finale. Every walk this lesson took had the same 2 ingredients. Stand on a vertex, ask for its neighbors. The order degree operation the adjacency list made cheap. To explore a whole graph, you need exactly one thing more. A place to keep the vertices you've seen but haven't visited yet. The frontier. And Lesson 13 already ran this experiment on trees. 2 traversals, identical skeletons, where the only difference was the container, and a promise that graphs would make the point sharper. Next lesson caches it. Feed the frontier to a queue, and you explore in rings. Nearest first, level by level, outward. Feed it to a stack, and you dive down one path as deep as it goes before backing up. Same graph, same neighbors question. 1 swapped container, 2 completely different journeys. They're called breadth-first search and depth-first search. They are the foundation under every graph algorithm you will ever run. And they're next. The last lesson. See you there.